Quantum mechanics is famous for its mathematical precision, but practically, nature only allows us to calculate exact solutions for the simplest, most isolated systems. The central equation of the field, the Schrödinger equation, works flawlessly when applied to theoretical models. If you want to describe a lone hydrogen atom or a hypothetical particle in a box, the math yields a perfect answer. But when applied to the physical reality of engineered materials, the foundational equation breaks down. We cannot solve the Schrödinger equation from scratch for atoms with many electrons, complex organic molecules, or solid-state materials. The computation becomes impossibly complex. To actually engineer devices like OLED displays or quantum computers, physicists have to abandon the pursuit of exact mathematical solutions. Instead, they rely on the science of controlled approximation. When the exact math hits a computational wall, we use two specific mathematical rescue operations to model reality. The first method we use is time-independent perturbation theory. This method starts with a simple system we already know how to solve and calculates how a small disturbance alters its energy and shape. The second approach we take is variation theory. When we have no exact starting point at all, this approach allows us to construct an educated guess and then systematically refine it. These two methods, calculating weak nudges and optimizing guesses, form the framework that allows engineers to step out of the idealized textbook and into the actual engineering of real atoms and devices. This illustrates the mathematics of small nudges. Instead of solving a complex system from zero, perturbation theory assumes reality is just a solvable Hamiltonian plus a weak disturbance. We use an anchor, the H0, then add the disturbance, scaled by lambda, to track its exact strength. We can see how this math operates in the simplest non-trivial quantum scenario, a system with exactly two energy states. Interacting quantum states refuse to cross. When coupled, they mix and undergo level repulsion. The lower state is pushed down, the higher state up. This mixing dictates how a qubit shifts under magnetic noise, or how molecular states interact inside OLEDs. To calculate the shift's magnitude, we use the first-order energy correction, which mathematically measures spatial overlap. If an applied field hits the exact physical region where the particle lives, the energy shifts dramatically. If it misses, the shift is zero. A perturbation shifts the identity of the quantum state itself, forcing real wave functions to borrow character from their surrounding neighbors. This approach is highly effective, provided the unperturbed system is a close approximation and the original energy levels are well separated. However, there is a boundary limit. We have to look at what happens when two quantum states share the exact same energy, a condition known as degeneracy. Correction formulas require dividing by the difference between energy states. When states are degenerate, that distance is zero. Dividing by this shrinking denominator causes the mathematical correction to explode to infinity, and standard perturbation theory violently breaks down. To bypass this, we use a rescue operation, degenerate perturbation theory. We construct a perturbation matrix specifically inside that degenerate subspace and diagonalize it. This forces the math to select the correct linear combinations, splitting the degeneracy and stabilizing the system. But what if you are evaluating a complex molecule where no exact solution exists to act as an anchor? Perturbation theory is useless without a starting point. Instead, we must guess. The variational principle states that a trial wave function's expected energy, the Rayleigh ratio, will always be greater than or equal to the true ground state energy. We optimize this by adjusting our mathematical guess, forcing the energy to drop lower on the landscape. The rule here is absolute. The lowest energy guess wins. This provides a strict upper bound to reality. To scale this up, we use the Rayleigh-Ritz method. Instead of a single rigid guess, we build the wave function from a modular kit of known parts, like atomic orbitals. Minimizing the energy converts the physical problem into a massive matrix diagonalization problem. We let algorithms crunch the matrices, choosing the absolute best combination of basis parts. This is the computational engine powering modern quantum chemistry software. These two paradigms sit at the core of applied quantum mechanics. Perturbation adds small corrections to known anchors, ideal for weak disturbances. Variation minimizes a guess's energy to approximate unknown systems, but perturbation fails near degeneracy, and variation depends entirely on the initial guess. These mathematical rescue operations, the closure approximations, the Rayleigh ratios, the level repulsions, are not abstract academic exercises. They are the operational backbone of modern applied physics and chemistry. We use them to calculate absorption frequencies for medical spectroscopy, compute bond energies for molecular design, map decoherence in quantum computing, and modify energy bands inside semiconductors. Final conclusion: because the universe refuses to let us solve its most complex systems exactly, engineers must rely on controlled mathematical simplification to step out of the textbook and into the engineering of real materials and devices.